what I want you to see is the values of S that make this characteristic equation equal 0 are the poles. The poles of the closed loop transfer function are the same as the values of S that result in one angle plus or minus 180. If I get plus 1 plus or minus 180 in GH, then 1 minus 1 is 0, I get the same thing. So the root locus graphical technique is to evaluate these phasors, LZ1 over LZ1, evaluate them and reason where this KGH equals 1 angle 180 comes from. It's called the angle condition. So if the angles, LZ minus the angles, LP minus the angle, LP, if these angles sum to plus or minus 180, I'm on the root locus. What's the gain? Well, if the magnitude of the gains times the lengths, if the magnitudes of the gains times the lengths equal 1, I'm on the root locus. So once you're on the root locus, all you have to do is solve this formula for KRL, and that will, summarizing, we're going to apply the angle condition and the magnitude condition, and then you can derive all the important root locus rules, of which you need to know 3. You need to know 3. So let's take an example to show you how this works. Here's an actuator. This is the actuator that you did in your lab 1. Okay? So there's your actuator, 20 over S plus 20 with H equal to 1. All right, so let's pick a trial point, anywhere in the S-plane. Anywhere in the S-plane, I pick a trial point. I want to evaluate that function at the trial point. So how do I do that? In other words, what is this LP1 going to be? I don't have any LZs. There aren't any zeros, but I have one pole. Well, it looks like S, the trial point S, goes like that. That's the trial point S. And then this is minus P1. So S minus P1, or S plus 20 plus S, is LP1. That's what I want you to see. For any pole or any zero, if I want to evaluate it at some point in the S-plane, I just draw a phasor from the pole or from the zero. That's the value of that polynomial at that point. You may not have had that last quarter. It's a shame if you didn't, because it's going to open up root locus tremendously for analysis. Once you see that, you can see that where am I going to get 180 degrees for theta LP1? Where's the only place that 180 degrees is going to exist for it? Obviously, this is not going to exist because minus theta LP1 is not equal to 180 degrees. Where would I pick my trial point for this value to be 180 degrees? This way. Any trial point is going to be on the root locus if I stay to the left of the x. Right? Because the angle is going to be 180. It's going to be so it's going to be minus 180, so it'll be plus or minus 80. It will be on the root locus. How about the gain? What will the gain be here? What will the gain? Well, I'm going to draw this trial point. That's going to be my LP1 on the root locus. Now, what's the gain going to be? Well, I go over here, and I see that it looks like the gain equals the product, equals the length. It equals the length of the... So the length of this guy is the gain. It's going to go this way, and as the length gets bigger, the gain gets bigger. Starts out at 0 and goes to infinity. MATLAB will often give you a root locus going this way. Right? It doesn't care. MATLAB is just going to blindly solve this equation. And if it gives you roots going that way, the only way you're going to catch it is to see it. And if you build a system like that and hook it up, you will hook up the flight controls backwards. Has that ever been done before? Almost. Done all the time. If your root locus is backwards, first rule, always to the left of an odd number of poles and zeros. That's the first root locus rule. And you can see it from this. If you put more poles and zeros in it, it'll fall in. Let's look at your problem. Readiness check. You have 2 poles at the origin. 2 poles at the origin. Where am I going to satisfy the angle condition for my trial point? Well, let's just pick one. Pick a trial point. I'm over here. I picked that trial point. Is that on the root locus? Angle 0, angle 0, 0 plus 0 is 0, not on the root locus. How about over here? Minus 180, minus 180, minus 180, minus 180 is minus 360, not on the root locus. Where do I have to go to get 180 condition? Yeah, if I pick a trial point anywhere on this axis, I'm going to have 90 from one pole. So I got 90 from one pole and 90 from the second pole. Minus 90 is going to be minus 180. I'll be on the root locus. So the root locus is going to look like that going up. One more thing. I put a pole here. I put my actuator on this system. So now I add this thing up. I get minus 90, minus 90, minus 10. Minus 90, minus 90, minus 10 is minus 190. It's not on the root locus. Where do I have to go to make this work? To the right, yeah? Here? Make this 85, 85, 10. 85, 85, 10 is 180. So what does that tell me about the root locus? I'm screwed, right? You see that? What if you put a 0 over here? What if you put a 0 over here? I pick my trial point over here. I got minus 90, minus 90. Now the 10 goes the other way. So instead of going to minus 190, I go to 170. I got minus 90 is 180, plus 10 is 170. How do I get 10 more degrees? Over here, right? Make this 95 plus 10 is 180. So I put a 0 over there and I go this way. I'm to the left of an odd number. There's 2. So there's no root locus here. So the root locus must be on this root locus. I must go this way and this way. So I can sketch the root locus before I even see what MATLAB's going to give me. Is this too simple for reality? Is this too simple? What do everything look like in space? Doesn't everything look like in space like torque equals J omega dot? Or theta double dot? Doesn't everything floating around in space look like that? What's the transfer function? Everything. Everything in space looks like this. So what happens when you put your actuator on your spacecraft? You put your actuator, your 20 plus 20 from your lab 1, you put it on your spacecraft. What do you do to it? It automatically destabilizes the spacecraft. So you can't put the actuator over here. That makes it unstable. So you got to place the poles and the zeros over here to get a reasonable root locus. All what I'm showing you here today, this graphically seeing this, if you practice it a few times, will give you enormous insight into what your MATLAB program is doing. And it'll give you simple solutions for control problems that work 90% of the time. It'll work 90% of the time without having to build and go into a complicated control scheme.